last class we started local list decoding. We have done unique decoding, we have done local decoding, we also did list decoding for Reed-Solomon. Now we will do local list decoding, and by this we mean the concept of finding again jth bit of x, message x, given a corrupted code word y, where the errors are less than rho. But now the thing is that rho can be very close to half. Okay, it can really be close to half in this binary code, which means that there cannot be unique decoding. So there may be many x's, and the idea is that given an advice what x through this string I0 or through this number I0, given this advice that I want or the user wants I0th x, xj can be found with high probability, and in very few queries. Okay, it should be a polynomial in log m n by epsilon time, where epsilon is how close you are to half in terms of errors. So what I said was that you can also ask for the, so you can think of I0 as the location of x, in the unknown list. There is a list of x's, and I0 you can think of as the location, and you can also ask for not just xj but the whole string x, assuming that it is not very long. So when n is, so n was the length of x, right. So when n is in terms of time, which is polylog m. So when n is equal to polylog of m. So which happens, for example, in the Walsh-Hadamard case, but it may not happen in Reed-Solomon, Reed-Muller case. So in case the blow up that the error correcting code is doing, it's too much, then you only ask for few bits of x, otherwise you can ask for the whole x, because it makes sense to output everything. Why just the jth bit? Okay, so advice is the only new thing which has been added here. Let's now start this for the maps that we have seen. So let us start with local list decoding, Walsh-Hadamard. I will not go into the full analysis because our time is up. Today is the last class, so I will only give you the core ideas of local list decoding, and then in the end we will finish the proof of average case hardness from worst case hardness. So the first local list decoder is for WH, given by Goldreich and Levin. So they say that WH is the map and F is the 2 raised to n bit string that you should think of as the corrupted code word given to you, be the given oracle. Such that there is a message x for which f and Walsh-Hadamard of x in the zth place, they are mostly equal, they match. Okay, so they match just above half. On more than 50% locations, Walsh-Hadamard of x is f. So that is what the setting is. Now there exists a polynomial time polynomial in n by epsilon time algorithm to find the list. The list is corresponding to f, what is the x, what x's are possible. So the fractional Hamming distance of f from WH of x, this code word is less. Okay, so there is a polynomial in n time, n by epsilon time algorithm to find the list. Notice that here we are actually outputting all the x's and full x's, not just jth bit, simply because x is so small that in polynomial in n time you can as well output all the bits. There are only n bits to output, right, for an x. So that's what the algorithm will do. So this is a local list decoder for Walsh-Hadamard. So local list decoder for number of errors this much. That's rho. Okay, so we can call this the local list decoder for Walsh-Hadamard. Okay. So the errors that it can tolerate is just below half. Anything below half it can tolerate. What is the idea? The idea of local decoder was randomly choose a location and then to find the jth bit, that location plus the elementary vector ej, right. So it queried two locations and from that it constructed xj. Since you want all the bits, many locations will be queried. And actually, oh yeah, the more serious problem is that the corruption is in almost half of the locations. So you cannot just randomly pick a place and hope to get xj with probability more than 2/3, right. You wanted probability more than 2/3, so that will not be possible now because already the error is close to half in y or in f given by f. So we will actually make more queries, and from many queries we will try to deduce xj, and then repeatedly by repeating that we will find x. So f is corrupted close to half we need more than 2 queries. And x is not unique. And LF is not a singleton, LF is long. So there are many x's basically. So we will what we will do is make many correlated queries. We'll make many correlated queries and we will guess the answers. and guess some answers. So this guess will be basically to using the advice, okay, from advice. Okay, so the advice, let us ignore that for now. In the theorem statement there is no advice, because here actually we are just we want to output all the x's, but according to the particular x you want to output, it will be obtained by a guess. You can think of it as the advice. That is the plan, vague plan. So let's implement this carefully. Let us define k to be log of m plus 1 where m is something like n. Okay, so k is something like log n. These many queries we intend to make. So randomly pick points S1 to Sk in the string y. So these are n bit strings, k many, randomly picked, and guesses sigma 1 to sigma k. For the, okay, let me write that down. What does guess mean? So we are hoping that there is a unique x in LF such that for all I sigma I is x Si. So in the SIth location of the correct code word, which you don't know, right? So in the correct code word we are assuming that the bit is sigma I, which means, if you recall the definition of Walsh-Hadamard, that the inner product of x and Si is sigma I. So let us make these k guesses. What is it that you have in the correct code word of related to x, WHX, right? So make these k guesses, and then based on this you do the queries. If this guess is correct, then you will be able to recover x. That's the plan. And 2 raised to k, notice 2 raised to k is around n by epsilon square. So that is supposed to be the list. Okay, so we are hoping that this identifies the unique x, sigma 1 to sigma k. And define ST to be the sum of SIs and sigma T to be the sum of sigma I's. Okay, bitwise XOR. For all subsets T. So for a subset T, now, for example, the subset 1 and 2. So for that, ST is S1 plus S2. and sigma t is sigma 1 plus sigma 2. This is done mod 2, okay, or parity or XOR. So we have these locations now to be queried, STth location in F to be queried. So let's query. So compute xi to be the majority over all t So basically you want to find xi, right? So you should use elementary vector ei. So you have already kind of guessed the value at st, which is sigma t, and you shift it by ei and query. So f at st shifted by ei. Where ei is the ith elementary vector. Right, this you have already seen in local decoder of Walsh-Hadamard. So do the same thing, except the only difference is that sigma t is not being queried. This is guessed. This is from the guess. And the query is only done on st plus ei location. And then in the end, output x1 to xn. So this actually do it for all I. For all I, compute this, and then you output these xi's. So this is one string that you have outputted. Now you can repeat this experiment or this subroutine. So when you repeat it, what will happen? You will make a different guess, sigma 1 to sigma k, right? So you do that, and you will output another, in the end another x1 to xn, n tuple, and so on. So if you repeat it enough, then hopefully you will get the whole list. That's the idea. So repeat the above algo for, let's say, 1000 n over epsilon to the 4 times. Okay, so hopefully this gives you the full list LF. Yeah, so that is that's the local list decoder. I would want to skip the analysis of this. But let me just say, if you want to see the analysis, in my old lecture notes, on the home page, or you can see it in the textbook. The main idea in the analysis would be to show that with the right guess, when sigma 1 to sigma k are correct, when guesses are correct, then this output is correct. It is in LF with high probability. Okay, that is what you have to show, but there will be a lot of probability calculation in this. Obviously, if the guess is not correct, then you will get either, yeah. So when the guess is incorrect, then what happens? Then you may get the wrong answer, but when the guess is correct, then you get the X, you actually identify a unique X in the list. So this will really depend on the guesses. You can think of the guesses also as a part of the input. Okay, hence it is a good local list decoder. Given the right guess, the right advice, then actually you get an element in the list, otherwise not. That is what you have to show. So now let us move to local list decoder for Reed-Muller. So here again you have to recall what you did for local decoding of Reed-Muller, right? So you drew a random line passing through the point you are interested in, and that then used Reed-Solomon decoding. So we will do a similar thing now for local list decoding as well. So recall that Reed-Muller maps L plus D choose D evaluations of a D degree L variate polynomial P to all evaluations. Okay, so these given evaluations L plus D choose D evaluations, the message that is essentially as good as giving the coefficient, so describing P uniquely, and once P is described, then the code word is all evaluations. Okay, so there is redundancy. And now when some of the evaluations, when part of the code word gets corrupted, how do you recover X or Xj? So now our goal is to output Px given X given a point in the space, an oracle to a corrupted code word, Reed-Muller applied on P, and an advice. Okay, so advice here will be a point in the space x0 and its value. That will be the advice. So you are given a point in space and you are given an oracle to P, RM of P, and you are given an advice string which is basically evaluation of P, unknown P. Now there may be many P's. What this advice will do is it will specify uniquely P. That's why you need this advice. And with all this, you want to output P of X. So given these three things in the input, you want to evaluate P at x. How do you do this? Remember that there are many P's possible because RM of P is corrupted so much, close to half. In fact, close to, in this case, it will be close to 100%, close to 1. So there will be many P's. There is a list, but this advice will pinpoint some P in the list, and for that P you want to evaluate no matter what x is given, P of x. This was done by Sudan, Trevisan and Vadhan. Okay, so Reed-Muller has a local list decoder handling close to 100% errors in the non-binary alphabet. So it's 1 minus 10 square root of d by q. Okay, remember that this is the non-binary version. So out of this F to the L evaluations, almost 100% field elements are erroneous. They are erroneous evaluations. And the field is large. The alphabet is also large. That is given by the finite field. So you can compare it with list decoder. Of Reed-Solomon. That handles 1 minus square root of d by q errors. Okay, so in that sense there is some restriction here. So Reed-Solomon could handle more errors. Reed-Muller local list decoder is handling fewer, but still it's comparable. Okay, it isn't so bad. It's in fact very good. So again, let's just look at the proof idea. We can't do the whole proof. So the idea is randomly pick a point. So remember, in local decoding of Reed-Muller, we drew a line. Now we will, so that was degree 1 object. Now we will draw a cubic curve. Okay, instead of degree 1 curve, now we will draw a degree 3 curve. So it's a cubic curve through 2 points. So one is this point x given in the input, and other is x0. So draw a random cubic curve through x, to be particular 0 comma x, and r comma x0. Basically, it's x and x0 is given. you want to associate x with 0 and x0 with something random, which is R. So, random cubic curve through these two, call it L x comma x0. Okay, it is a cubic curve. So, L x comma x0 has points it will have points qt, q1t to qlt, okay, for all values t in the field. That is the set of points you are looking at. It is in the space f to the L. So, q0 is basically the point x and qr is the point x0, that is the meaning. So, it is a subset of f to the L and qi's are cubics. Okay, so, in this space you have drawn this parametrized cubic curve. It is parametrized by t and t takes all the values in the finite field. And q0 is x and qr is x0. Remember this, which we say that the cubic curve is passing through x and x0. Now, query f is the oracle given to you, right, to the corrupted code word. It is basically, you know, evaluations of p, but many of them are corrupted, close to half of them. So, we will only look at those evaluations which are at the points of this curve L. So, query f on L x comma x0, run Reed-Solomon list decoder to find a unique GT so on QT evaluations of P will be P of QT, and as you go over all the T's, this gives you a polynomial GT. This will be unique because P is unique at the point x0. So, GR is P of QR, right, which is P of x0, which is y0. So, since y0 is x0 y0 is given to you and it uniquely specifies P in the list of correct P. So, actually P is unique and G is unique, and the Reed-Solomon list decoder will give you this G, and then you output, once you have the correct G parameterized by T, right, T is a variable here. So, you can actually now evaluate for T equal to 0, that will give you the point x on this curve. That is the answer. So, you can output this. Okay. So, the picture that this requires is we have drawn a curve which has x0 and it has x and it has this general T going over the field element, and that's your L. Okay, we were interested in basically it had to pass through 2 points and still have some freedom. So this is why we needed degree 3. And remember that this happens in a finite space. So this space is f to the L. Okay, all this happens in the space f to the L. This is a very discrete object, but analytically you can think of this. In the input you are given oracle f such that the probability, and basically f should, evaluation of x on the point should match with px. On a lot of points, but this is much less than half. Okay, so actually f and p don't match on nearly 90% of the points, and they match on this much, 10 square root of d by q, and we take the size of the finite field to be more than d to the 4. This is given in the input, advice is given, right, this we said in the idea, and x is given. In the output you want evaluation of this unknown p on x, so a field element. So the decoder is as follows. So pick a random field element R and monic cubics QIT where by monic we just mean that it's the t cube coefficient is 1, and then there is t square coefficient, t and constant coefficient. So there are 3 unknown coefficients such that qt which is basically L tuple satisfies q0 is x and qr is x0, right. So it's a random cubic as we said before, passing through x and x0 basically. Next you query f on this L, right, all the evaluations q of t for all t in the finite field f. So query f on this, to obtain these tuples. So when you query f on a point qt, you get a value in the field, right? So you have collected all these size of f many evaluations. Now many of them may be wrong, right? Given the property of f, many of them may be wrong. But then you can list decode using the Reed-Solomon list decoder, and with the input guarantee you will be able to get a list of all the p's, out of which one will be identified because of this advice. So run the Reed-Solomon list decoder on S to find the list G1 to Gk of polynomials of all degree 3D polynomials, 3 times D polynomials, that agree on greater than 8 DQ pairs in S. Okay, so overall f agrees with p on 10 square root of d by q points, and here we are asking for 8 square root of dq. It's slightly less, so this is there is a good chance that this will happen given the guarantee on f. There is a good chance also because the cubic curve was picked randomly. So there is a good chance that this distribution will be there and you will actually correctly get G1 to Gk, out of which one will be right. So you pick that one. So if there exists a unique I such that GIR is equal to Y0, then you output GI0. Okay, because out of this list G1 to Gk, this is the right one. This will happen with a good probability, good chance, else you have failed. Okay, if there is no GI which is giving value Y0 at R, then it means that this experiment was useless, so you have to repeat or just output fail and exit. But the probability of that will be less, will be small. Okay, so the analysis I am again skipping, so read the analysis if you want. Okay, so that is essentially the local list decoder for Reed-Muller, drawing a random cubic curve and then doing Reed-Solomon list decoding. Finally, we combine the two. So again, it's a theorem by Sudan, Trevisan and Vadhan as before, same paper, which says that in general, instead of Reed-Muller, think of code E1. Okay, so n is stretched to m alphabets, n bits stretched to m alphabets, and E2 is like Walsh-Hadamard, so it will convert alphabet to bits. So say these are error correcting codes with local list decoders using advice from index sets I1 respectively I2 and handling one minus epsilon 1 respectively. So for the non-binary it's 1 minus epsilon 1, for the binary E2 it's half minus epsilon 2 errors. Then you can combine the two. Then E2 E1 error correcting code E has a local list decoder using advice I1 cross I2 right in this product, and handles so how many errors? It should be some type of a product, right? 1 minus epsilon 1 times half minus epsilon 2. But what you have to be careful is, just like local decoder for the composition, goal will be to actually find the alphabet, the letter in sigma completely. So when you apply the local list decoder for E2, you have to pay more. So you will pay this factor of I2. So it will be this. So actually to get what advice to pick from I2, you will try all the advice actually. So as many advice strings there are in I2. So that price you pay, and for the binary it is half minus epsilon 2, and then you take the product. Okay, this proof is actually similar to the local decoder, and I'll completely skip that. Similar to local decoding. Okay, so finally we have finished local list decoding for all these maps. What do we have now? So now all that remains is to apply this to get average case Hâṛ function. So from this we now deduce that for a worst case hard f, Boolean function f, if you apply on the truth table Cf as a string, which means truth table, its truth table, and then apply concatenated code on this. And see this as a truth table of a new function g. So, this is the truth table of an average case hard function g, right. Why is that? Intuitively, because if G is not average case hard, then there is a circuit which can compute this on significantly more than half of the input cases. So, now the truth table of that circuit you can think of as a corrupted code word. And from that corrupted code word, when you apply the local list decoder that we have just built, then you can evaluate f on x. That is the idea. Otherwise, the circuit C approximates G, okay, and think of the truth table of C as a corrupted code word. As a corruption of this. In truth table of C you have oracle access. So, now apply local list decoder. Applying the local list decoder of Walsh, Hadamard, Reed, Muller on this oracle. In fact, let me just say oracle is C. On oracle C, we compute f on x. Okay, for any x. Now, the C is an oracle, it is a circuit, small circuit in fact, and the local list decoder is an algorithm which is very fast. So, that also is a can think of as a small circuit. So, overall you get f circuit for f. Okay, which is a contradiction. Okay, that is the idea. So, in the proof details you have to look at the algorithm local list decoder and convert it into a circuit and check the parameters that you really get a polynomial sized circuit. Moreover, it's the advantage over half should be significant. Okay. So all those things you have to, or well, the advantage over half should not be significant, in fact, because you want to prove that G is average case hard. So those things you have to look into the details. So let me just state the theorem and then stop. Hardness amplification. So this theorem is by Impagliazzo-Wigderson. They proved it first in 97 by combinatorial methods, and then this error correcting code based proof was given by STV in this paper that we have been talking about, Sudhan, Trevisan, Vadhan from 99. Okay, this was an algebraic proof to amplify the hardness. So if f is this exponential time computable Boolean function which is hard, circuit hard, for some s, it's harder than, let's say, S of n, that's the hardness, worst case hardness parameter. Then there also exists in the same complexity class E, there is a function g and a constant c such that the average case hardness of G is similar. For large n. Okay, so for large n, G actually looks hard as F, but in the average case. Okay, so it's much harder than F, and it is in the same complexity class E. We will we don't have time to do the proof of this, but it's based on just applying the local list decoder. So analyze the parameters of local list decoder of Walsh, Hadamard, Reed, Muller on corrupted version of Walsh, Hadamard, Reed, Muller applied on the truth table of F. Okay, so that is the code word, and then it is corrupted, and the local list decoder wants to get back to F, some location in the string TTF. So you have to analyze the whole thing, all the parameters, and you will get this. Okay, so left as an exercise. Okay, so that finishes a major theorem in complexity theory, and with that the course ends. I hope you enjoyed the course. Thank you.